So my name is Tudor. I'm a Director of Technology at Filtronic. And really, at Filtronic, I've been there for 2 years now, and my role really is strategic, to look at future direction of the company, future product development, looking at roadmaps and what we can do differently. And today I'm going to talk a bit about what we do for low cost and high volume. I guess it depends what you define as high volume. Maybe it's not high volume for everyone, but for us it is. So we produce these transceivers for the backhaul market. And probably in the range of 1 to 3,000 a month. So quite high volume for just the kind of complexity of transceiver. And these are quite difficult to make. So they're high frequency, they're E-band. So it's 71 to 86 gigahertz. So that's quite complex in terms of design, but also design for manufacture, how we do that properly to make sure we can repeatedly do this over and over again. So I'll start. I am going to talk a little bit about Filtronic because I think everyone probably knows Filtronic, but we've gone through so many changes over the years. It's worth just refreshing people of what we actually do today. People still think we just do filters, and that's probably not the case. So the name goes against us on that one. Then a little bit about introduction in operating in a low margin market. How do you do that? So it's not an easy thing to do, as many of you probably know. If you work in comms, then it's a difficult market. They're always driving down cost and price, and they expect you to be able to achieve sometimes quite ridiculous price points for the product. A little bit about our older product, Orpheus, then how we redesigned that to make the cost lower. So I guess as Filtronic, what we try and do is operate at the cutting edge. So we operate in the newest bands possible for the backhaul market. That's what we're talking about today. So at the moment we're E-band 71 to 86. We're already developing the next stage of that to W-band, which will go up to 110 gigahertz, and then looking beyond that, probably to 170 gigahertz for D-band. And what we have to do is keep ahead of everyone else. We're UK-based. We do have price points that we can meet, and we're very skilled. But we have to be at the cutting edge because they'll pay while it's new and while nobody else can do it. They'll pay good money for it. And what we have to do then, as that sort of stabilizes and as we go through that market, we have to push down the price of that product as well. So that's kind of where we're looking at today. Something on the high power variants, that was the hardest one to do actually. So I'm talking about different configurations of transceiver here. They all have to have the same footprint, but have different functionality. I'll talk about the different variants we can do in that same footprint. And it's trying to make as much commonality as possible, I guess, within those variants as well to get the cost point right. Some then about the ultra high power variant. I think that's on display outside of the old Hercules 2. We have a new design of that as well for the same reason, trying to push down the cost and make manufacture easier all the time. And then a bit about the future, if I have time. So I'll keep an eye on my time. So here's the very brief introduction. So we've been around for about 40 years. We actually span out of Leeds University in the 70s. And that was a filter company at the time, hence the name Filtronic. But over the years, we've done various things, and we grew very big at one point in the telecoms bubble, and even owned our own fab for manufacturing gallium arsenide devices. We kind of decompressed from that now and sold off lots of bits of the business, and refocused the company now to a fairly small 120 people, but growing year on year actually, and growing in revenue and people at the moment with some new market stuff. I'll touch on that a bit at the end as well. And we kind of work everywhere in frequency, anything from megahertz right up to over 100 gigahertz. So we cover quite a lot of ground. And all to do with signal conditioning, so filtering, signal conditioning, transmit and receive modules, so power amplifiers, transceivers, low noise amplifiers, anything in the RF front end space that sits between the antenna and the digital end of things. I think I got a slide on markets there. Yeah, so markets for us, as I say, we cover the whole spectrum there. Critical comms at low frequency in the megahertz range. That's still a big part of our business, actually, probably, I think, a third of our business, and that's really push-to-talk type networks. We do tower-top amplifiers, signal conditioning, filters, diplexers and stuff for that market, mainly in the US, actually, and we have a US company to do that. Aerospace and defense remains a core part of our business. Obviously, we have UK manufacture, and that's really important for the defense companies to have that supply chain within the UK. And we do various things for those guys. We do custom filter design. We do just manufacture, build a print type manufacture for their systems, and produce things like TRM modules for ESA radar for some of the big primes. Space is our newest market, and one I've focused on probably since I started fairly heavily because it's a new and growing market. really disrupted market actually as well because of the new space movement with these LEO's constellations, which really changed the landscape for space. You know, companies have been around for a long time doing space business, but they do it in a very expensive way. You know, so they had these products which were one-off satellites that would last for 40 years and would take 12 months to build. And now that whole landscape is flipped, where we have, you know, anything up to 10,000 satellites in a constellation, and they want the price point to be probably a tenth of the cost of what it was before, and they want it delivered in 18 months, not in 10 years. So the old space players find that quite hard to deal with and quite difficult. And what we found is, because we do these transceivers on the ground for backhaul, like I'm talking about today, we've had companies coming to us and saying, could we translate that into space products? And we've had some success already in doing that. So we're already supplying power amplifiers, for example, in the ground stations, and starting to work on payload as well for that. So today we're talking about telecoms infrastructure. As I said, we've been playing that game for probably 20 years plus. Typically on the backhaul side, so looking at those high data rate point-to-point links. And as I said, we have to keep at the forefront of that. So you have to be always pushing the hardest bit to do. You know, we win by being at the cutting edge and the most challenging bit of design and the most challenging bit of manufacture, because not many people can do it. We can actually make a profit and be sustainable in that area. And then test and measurement is kind of a side one. We don't do that much in test and measurement, but we can. And same sort of components used in test and measurement as the other markets. So what do we need to do to operate in a low margin market? I've said the first one already a number of times: do the hard things. You have to do the bits that nobody else really wants to do. And even the big companies don't want to do it because it's too difficult for them. It takes too much design effort. And that's how we can stay at that competitive edge of things and try and make enough money to sustain ourselves in this comms market, which is very difficult right across the whole board. So vertical integration, owning part of the system and key parts of the system and the key IP. And Liam was talking earlier about custom mimics, and that's one thing we do within our products. So we do our own custom mimics. We have designers in-house, and we manufacture them in a fab in Taiwan. And I think really to hit the margins that they want, you have to do that. So there's two reasons to do it. Number one, it's cheaper than using COTS. And every penny counts on these things, really. So, you know, you're probably half the price to do your own custom mimic compared to buying off the shelf once you get decent volumes. But also performance is key. You know, so we're trying to differentiate ourselves as well in the market. There aren't that many players, but there are other players. And if we can do our own mimics, we often find we can do better in terms of performance than the competitors and get a market edge there. And people are willing to pay for it. You know, they will pay for an extra dB of power in the companies. They know it's important, and that has an overall impact on system cost. You know, so a bit of extra power goes a long way. Designed for cost and performance, and they're quite often competing against each other. You know, because you want very high performance, very good performance, and high spec, but it has to be at a price point that you're realistic. You have to be able to sell it at the end of the day. And I've had many conversations with engineering teams in the past about that, because engineers want to do the best job they possibly can. They always want to do the utmost to get the top performance they possibly can. And you have to sit them down and say, we need to be able to sell this thing as well. It has to pass the, you know, can we sell it test? So you look at, you know, where corners can be cut that don't impact specs. You know, so they get very close to the specs maybe, but you have to work out where those corners are. What bits can you change? What bits can you mold to make the savings? You know. And design for manufacture. So I said that it's not just the cost of the bomb. So the bomb's important, obviously, and the bits that make up that thing and which you have to buy in are important. But it's also how easy is it to put together. You know, if it's really cheap, it's really difficult to manufacture, or you get terrible yield because of the manufacture, then you're not winning the game anymore. I mean, it's not really the way to go. So you have to kind of analyze this thing from can we produce it, can we design it, can we manufacture it, and we're lucky in Filtronic really because we have everything in-house. So we have the designers there, we have process engineers who look at then how we'd actually do die attach, wire bonding, how it all works together, and then we have the manufacturing line downstairs, and we're all sort of co-housed together, so we can have that constant feedback through the system without having to go to external companies and have that conversation. You know, we don't get much finger pointing. It's a conversation, and I think when you use outside companies to do that stuff, it's quite often blaming each other and saying, "Well, that wasn't my fault. That's your design." Oh no, it's not. It's your manufacturer. We have this, this game to play, but we're lucky in Filtronic for that. And then the bit we're talking about today, I guess, then design for configurability. Think about the future. So when you design your product, don't just think about what you're doing now, but where it might go next. So try and get building blocks in there. Try and think about if it doubled in power, what would I do? How would I do that? And that's not something people do very often. You know, we tend to, as engineers, want to say, again, want the best solution we possibly can. And that we may have to make some compromise. If we want to have a building block approach that can be configurable later on, we may have to have some compromise there. And that's something that we need to think about when we do this stuff. So here's an example. So this was our old Orpheus product in blue there, and where we started the journey at E-band. Oh, I think it's second generation actually. And that actually has an internal RF board underneath the electronics there. So there's a high cost RF board in the middle. And then a diplex underneath. So you've got metal plate, which is really just to support the circuit and thermal management, and then a diplex underneath. And then we looked at that and we're asked to reduce the cost. I think by about a third. By the OEMs we're selling to. So we had to reconfigure it and think, well, where can we make cost savings? And one of the biggest ways we did that was to actually put alumina tiles with MMICs instead. So you can see the metal housing. I don't know, I got a laser. Yeah. So the metal housing here, and underneath there are our custom MMICs. So we have a up converter, we have a LNA, a PA chain as well, a transmit and receive chain, all custom in-house. But we've now gone from a whole RF board this size, full size RF board with all the chips underneath this, to this very small area of alumina tiles just sat on top of a normal standard PCB board. We've also reduced the size of the diplexer underneath. So the diplexer sits about this area here. It's a very small metal plate underneath, which again reduces cost, even the metal costs. You know, so if you can get the area of that metal down, that helps on the price, and also you can got complexity of that as well. So if you keep that as simple as possible in terms of the waveguide combiner, that really helps on cost as well. The more complex you make that, the more cost you add in. So that one I showed on the right-hand side there, we now have 8 variants, all with the same footprint, all look almost identical, actually. And I say we was thinking about that configurability when we did it. The simple ones are low band and high band. So we operate in E-band, 71 to 76, 81 to 86. And they can swap where the transmit is. So you can have it at low band, 71 to 76, or 81 to 86. And when we did our design work for the MMIC, we found that we needed to really split that band. You can get MMICs that cover the full band of 71 to 86, but if you want high performance, you tend to have to do that over a narrow bandwidth, which gives you more power or better noise performance. So they're the simple ones to do. So we just pick the right component, either high band or low band, LNA and HPA, and you can swap that out and make your new system. We then have some enhanced noise figure performance ones where people are asking for better noise performance. So again, we can pick a different LNA. Our standard versions of gallium arsenide, that's designed in-house. If people want better noise performance, we can buy a COTS part in indium phosphide and drive down that noise figure for them. And then the harder one, which I'm going to talk a bit about today, was they came to us and said, well, could you double the power but keep the footprint the same? So how do we do that? I guess we scratched our head for a bit, but we are now a variant in the same footprint that has twice the power. So we have a standard version at 27 dBm and an enhanced version at 30 dBm. So here's the low power and high power variants side by side. So again, exactly the same footprint. That's important because they're going in an outdoor unit for these customers. They don't want to have to change anything. You know, they want to keep the system around this exactly the same if they can. So we're trying to keep everything in clean and port positions the same. This now has a slightly enhanced metal cover over the MMICs because we're housing now a combination of 2 MMICs, 2 power amplifier MMICs, waveguide combined within that structure. And again, to minimize the cost, the back still looks the same. So that was, remember the diplexer before, so that was diplexing the low band and high band. That also now has the waveguide combiner for the power amplifiers in it as well. So same piece of metal, trying to reuse as much as you can to try and get the cost down. Have I missed anything on the slide? Yeah, not really. So I think the point is there, the combiner. You know, if you're going to put 2 devices in there, you better make sure you don't chuck away the power when you do combine. So you need something really low loss in terms of a combiner to get the full benefit of that system. And luckily enough at Filtronic, we've had quite a lot of experience at combining amplifiers. I'll show you at the end some of the higher power amplifiers that we've got that combine lots of MMICs together. And we use something called a magic T combiner. So in waveguide, very low loss and good isolation on the ports. And you can use it in two different ways. So I said there are two modes of operation. So you can get injection into the in-phase inputs, which give you a H-plane combine, or you can inject into the out-of-phase inputs. So out-of-phase signals into the inputs rather and get E-plane combine. So that lets you decide whether you want to combine in a horizontal fashion or vertically through the structure. So you can choose how you want to combine these things and where you want to place things. So we wanted a H-plane combine, so we needed a corresponding 0-degree splitter at the input. So we have a 0-degree splitter. So obviously in our world, the magic T is lossless. It's not though because of different things. The matching of the different ports is really important. Any phase imbalance will obviously cause you problems. So if you don't split your signal perfectly, you'll get phase imbalance and it doesn't combine fully. And then any isolation is really important. And particularly on the amplifier ports, you don't want the amplifiers cross-talking with each other and pulling each other around. It's causing you big problems. And the other big impact, I guess, is manufacturing and assembly quality. So the manufacturing is really important. We're obviously talking about very high frequencies. So the tolerance has to be very, very high. And we typically work to plus or minus 5 micron on the machining. So quite high tolerance. But things like surface roughness will affect things like this as well. So your waveguide combine, it's a very high tolerance process that is required. Thermal variations of thermals will affect this as well. As it heats up, the waveguide will change slightly and again cause problems. And then you have to improve the isolation. So we use an absorber on the port that's not used, so you don't get power bouncing back towards other things and causing problems with that. So here's a few results for the high power variant, Magic T. So we get about 0.4 dB loss in the combine, which isn't very much at that frequency. Actually, it's a pretty good result. The simulated value is about 0.15. But again, that doesn't take account of things like surface roughness of the metal. So we expect to see that come down a bit. You get a bit of spread as well, but not too much spread, but you get some spread there. And that's all to do with that manufacturing tolerance. You know, so this is really fine proportion waveguide. So any small differences will make a big difference in the actual combine. But yeah, as I said, Robin, they're still considered very, very low loss for this high frequency and achieved in a very, very small area, important as well, because we couldn't grow the circuit, as I said. So we had to do this all within a tiny area of the waveguide. Other bits then, so what I got here, I got isolation, so better than 20 dB isolation, which is a good one. And what we found, as I said there, is the quality of that isolation was pretty dependent on that isolated port and using a good absorber. And that's actually a manual step, so that's the one that's a bit difficult to do in volume manufacturing. So, but one we have to pay the price for because it's so sensitive to that. We have to use a hand assembled part for that one. And then we've got the performance in terms of S11 there, so a good return loss. So on the waveguides obviously is on the output of the PA, where you need low loss, and then you want a planar split again for the input side. You can split two devices and then combine back in waveguide. So we went for a Geisel splitter. So the closely related to a rat race type splitter, has 5 ports. And then you can use external terminations as well, so it's much less sensitive to parasitics. So it's realized on 5mm alumina, so using alumina tiles again, like we had for the other parts of matching. And then you have to pick the thickness is important of that. So when you're looking at that, obviously the thickness affects the width of the RF lines that you're going to develop, and also you want it to match up pretty well with the gallium arsenide devices you're going to be bonding to. So you don't want to make it too thick or too thin to try and minimize that bond wire length and remove the parasitics in that as well. So you want to try and get that as tight as possible. So that seems to be the best compromise. 127 micron 5mm alumina. So compromise between keeping those lines, which are starting to get actually pretty thin, as you can see. Yeah, we don't want much thinner than that. And actually keeping the height difference between the two parts as close as possible. So as Liam was pointing out earlier on, we was looking at the packaging, you need to design these transitions in a very accurate way to get good performance. And he was talking about 28 gigahertz. We're talking about up to 81 gigahertz. So that becomes even more important. So you have to really take care in your EM simulations and then start to match these transitions. You can see, again, like Liam showed, I think before with the packaging, you end up with these matching elements around the bond wires to try and cancel out the parasitics of the bond wire and try and get the performance optimized. I think there's another slide which explains this better. So what does that look like when you get the lid here? So this is the base, sorry. So your PA sits in this little bit here. You then got an extra bit of line here, so you may wonder why that's there. That's to allow some separation, so we can actually keep the devices apart. So we've got a driver device in here, and we want that in a separate pocket, ideally in the aluminium, to stop any modding or in any oscillations that might occur between the devices. So you're trying to get that in there. So this actually sits in a little tiny pinhole between the devices, so you get really good isolation in terms of performance on that. So I don't think I have any measurements for this one, but I've got EM simulations of what we achieve with that. So really good amplitude imbalance, the 0.2 dB, and the phase imbalance of less than 10 degrees, and the good input and output matching, and isolation of around 20 dBs again. So good performance for the 7176. When I'm on to the final results of the module, so we were looking for as close to 3 dB improvement as possible. And we get that, and a little bit extra, actually, interestingly, but low power variant this year in terms of IMDs, and then the high power variant here, and we see this sort of 3 dB improvement in output power. And again, all 8 variants, sorry, in same footprint. I think there's something like 95% reuse of all the components. You're trying to keep as much commonality as physically possible in that design to try and keep the performance going. So then on to higher powers. So and talking about building blocks and trying to build products from that. This thing here uses the same sort of waveguide Magic T combiner. So this one actually has 8 MMICs. So it's got 2 MMICs on each side. And within this core structure here, we have the same Magic T approach, combining 8 devices, again with very low loss, so tenths of a dB loss within that structure. It's a standard transceiver model I talked about already. If you put these two things together, what you get is a very high power transceiver. It's not typically used for telecoms, because the telecoms have limits on what they can actually emit. So it's typically used in private networks. And interesting, one of the big users are high-frequency trading networks. So people doing high-frequency trading, so they want the lowest possible latency, and the best way to do it is in the air. So fiber is slower than air. So they have these links, short hops, and they get from New York to Boston, or try and get the trades done in the fastest possible way. And they're willing to pay, and they will upgrade these networks as often as you can make them. If you get better performance, different frequencies, they'll buy new ones and strip them out and have the best performance, because everything turns into money for them. So interesting little side market for these sort of products. But yeah, again, it was about thinking about these things before we did it and how we assemble them. I think there's a version outside, which was the original high power variant, which was actually made as an engineering sample. So Andy Tucker was asked to put something together just as a demonstrator, which he did. And then, of course, the sales guy went off and sold it, and sold hundreds of them. And he's like, you can't sell it. It's a nightmare to assemble. So thankfully, after about 18 months, 2 years, we've actually redesigned that. Now we have a much easier to assemble part. And Andy can finally put the everyone to rest and stop doing the kludge that he had before to try and do a demonstrator, which was then sold. So I think I'm close to time. How long have I got?
4 minutes.
4 minutes. Oh, there we go. So I should be just about on time. I won't keep you from lunch, so I'll be quick with this stuff. So what's the future? I mean, I've mentioned it earlier on. I think that we're pushing up, and we have to remain at the cutting edge. We're market leading at E-band, but we're looking at the next band up already. So we're doing chipset development at W-band. And you can see where W-band sits at 92 to 114 gigahertz. The W-band stuff is interesting. It's split up in a slightly inconvenient way. So you get more bandwidth for W-band, but because of the way the bands are positioned, we'll end up probably with the same data rate. We'll still end up with 2 gig channels probably, and the same data at 10 gigabits per second, sorry. So what we're trying to do in that format is make exactly the same footprint again, so they don't have to change the system. So for W-band, it's going to be form factor fit. So the modem is the same. You can see the same modem, but just change the frequency. So again, it's about trying to think about commonality from our side, but also for the manufacturer, the other side. So really important for them not to have to change the system. And then D-band, beyond that, that's the next big step change. That's where you're going to see real bandwidth opening up. But of course, working at D-band is difficult, and we're not set up yet to do it. We started research. We've done some work on, transitions and things like that, but even wire bonds don't really work at D-band. The level of matching and tuning required would mean hand tuning everyone, and we obviously can't do that for volume. So you have to think about different approaches, things like flip clipping and hot wires or some other way of connecting devices that we haven't yet thought of. I mentioned space a little bit earlier on, and I play in that. That's fairly new for Filtronic, but we've made some really good success there. And we're starting to develop a portfolio for ground and payload-based systems. I think I've got a slide here somewhere, have I? Not really. I'll come to at the end. There's a roadmap slide quickly. So telecoms, direction travels there already. W-band, and almost recreate the same product lines. So the same transceiver, the same high-power amplifier, terrestrial combined ones, and also the high-power variant for high-frequency trading type networks. So they'll want W-band as well when it comes along. And then D-band operating below that at the moment. And the biggest problem with D-band really is there's no semiconductor devices that exist yet that will give you enough power to form a proper link. So if you need a 1 to 5 kilometer link, we just don't have the power there yet. But it's coming. And I think D-band will be probably conservatively 12 to 18 months away, I guess, before we start to see gallium arsenide devices with enough power to start to do that stuff. So we need to start thinking about the rest of the system and how we do that at volume, which is always difficult. And then space, I told you I've been working pretty hard on this, and we have quite a big roadmap for this. We're doing some really interesting stuff with device combining based on that waveguide combined technology I talked about before. We've actually got to the point now where we combine 32 MMICs, so 32 gallium arsenide MMICs at E-band, which gives you 20 watts PSAT at E-band. And the market we're going after there is really the ground station market. They're looking for more power, so we're using gallium arsenide devices at the moment. Gallium nitride now is starting to push to that limit as well, so we're starting to see devices in gallium nitride at lower node, let's be below 100 microns, which will actually get up to E-band. So we're starting the program now to develop GaN at E-band as well. And with that, we'd expect to get to probably 70 or 80 watts saturated power for the same sort of amplifier. That's starting to displace then traditional TWTs, which are being used at the moment. TWTs are very expensive, they're very complicated, they're hard to make. And from the conversations we've had, they're in the range of £250,000 to £500,000 per TWT at E-band. So for ground stations, it's very expensive, and we think we could probably do that at maybe 20% of the price. So interesting play into that market. We're also doing stuff on payload. I'm going to be very quick now on the last minute. Payload stuff is funded by ESA. So I've been working since I started forming links to UK Space and ESA. They've given us a contract for £3.7 million to develop transceivers at Ka band and QV band. So QV band is really the next band that I think will be exploited for space. It's such a dynamic market, though. It's moving so fast. It's moving faster than telecoms. The pace of change in this constellation space is massive, and we're seeing that real drag for suppliers like us to move quickly. And then just some supporting stuff in the bottom there. So talking about device design, MMIC design, and that custom stuff that Liam was talking about earlier on, and how we play into that and how we build things. And we're finding even for space, the price point that they're pushing for means you need custom MMICs again. You need to have your own gallium arsenide or gallium nitride to really play in that cost base. Thank you very much.